Hello everybody, welcome back to another Engineering Statics lecture video. Now in the last video we talked about and introduced shear and bending moment diagrams. And I know I caused you guys a lot of heartache, it wasn't too much fun, but don't worry, I have a solution. At the end of last video we said that this method where we cut the beam, no one likes to do that because every time we cut a beam we need to draw a free body diagram, we need to go through equilibrium equations, and it's just time consuming. It's not difficult, you guys are all extremely smart students, but again, it's time consuming. So what we're going to do is we're going to introduce a super secret to you guys. And you guys probably picked up on this. Again, you guys are the smartest students I know. And that is the idea that the load, the shear, and the moment are actually all related to each other very nicely. And if we know one, then we can figure out the other. And then if we know that one, then we can figure out the last one. How does this work? Well, if I know the loading scenario, which is something that will always be given to you, so that's always good, I can easily figure out the shear. And if I know what the shear is, then I can easily figure out the moment. So this is going to be a very quick way to solve for shear force and bending moment diagrams. Now this video might be a little bit long. That's typically what happens because we have to draw diagrams. So sit back, relax, grab yourself some popcorn, maybe yourself a nice drink. All right, so let's begin. So shear force and bending moment diagrams. And we said that, all right, we know what these are. They're basically a way to determine the shear force and bending moment throughout the entirety of our beams. And we said that the way that we analyze them is we actually cut them at an arbitrary location and then analyze the forces. And we said, all right, well, this is great. But the problem was that for every time we had a discontinuity, we'd have to make a new cut. So at the end of last video, we looked at this beam and said, all right, every time the loading path changes, I need to mark it down and kind of see, all right, where my cut's going to be. So in this case, we figured out that these were all the loading changes. We had the start of a distributed load, the end of a distributed load, every time we have a point load, etc. And we said for the regions in between each one of these changes, we would actually have to have a separate cut. So for this beam using the old method, we would need 6 cuts to obtain a complete shear force and bending moment diagram. Now you guys are probably saying, Clayton, they would never ask for a beam like this. This is too much. Well, I'm here to be the boogeyman of statics, but this type of beam with this amount of loads, this is fair game for a final. And the reason why is because professors would never expect you to cut this beam 6 times. There's again the secret where there's a nice relationship between the shear force and bending moment as well as load that can actually allow us to solve for this diagram very, very quickly. Now, the reason why these relationships are so nice is that we don't need to cut the beam. And if we don't need to cut the beam, this means 2 things. One, we don't have to draw free body diagrams. That'll save us a lot of time. And the second one is we don't have to keep doing force equilibrium. Again, that'll save us a lot of time. It's one of those things that once we see the relationships, we can just look at this beam and we'll know exactly how it behaves. So let's talk about the first thing. There's going to be basically 3 things that we're going to learn, and this is the first thing, and this is the easiest thing. It's when we have a concentrated load or a concentrated moment. As we said before, they disrupt the continuity of our beam, and they must be considered independently. So this is kind of the first little tidbit of information that we are going to get. So let's start off with concentrated loads. Now it's actually very simple, very intuitive, and you guys may have already picked up on it in the last video. Concentrated loads simply jump our shear force diagram up and down. So here's the first key. Concentrated loads, they impact our shear force diagram. And all they do is jump it up or down. So if we had a beam like this and we had that concentrated load of 10 and we were analyzing the shear force diagram at this point, the only thing we would have to do is say, all right, our shear force is at 5. Once we hit that point load, we actually have to drop it down by a magnitude of 10. And after that, we can just carry on with whatever we're doing. So again, the key here is the amount of the drop is equal to the magnitude of our point load. Now, this is actually very simple to memorize because if we have a downwards force, well, we're going to drop our shear force down. If we had an upward force, so in this case a support reaction, we are going to jump our shear force diagram up. That's it. That's all. Concentrated loads, the simplest thing. You guys probably already know this from the last video. I didn't even have to tell you guys. Now here's where things get a little bit tricky. Just a little bit, but again, you guys are super smart. Won't be a problem. Concentrated moments. Now, these are almost identical to concentrated loads. where a concentrated moment will simply jump our bending moment diagram up or down. So concentrated loads, they impact our shear force diagram. Concentrated moments, they will impact our bending moment diagram. So if we had a concentrated moment on this beam of 10, and we were to draw our moment diagram, at this point right here, once we hit that concentrated load, we would actually have to drop down by a magnitude of 10. So again, the amount of the drop, 10, is equal to the magnitude of our concentrated moment. Now this is where, again, things get a little bit screwy with you guys, because you guys are saying, Clayton's drunk. Obviously, look at this. We have a positive moment, right? Positive moment because it's going counterclockwise, but he dropped it down. No. This is the first thing that will always get students. A positive moment in this case drops our diagram down, which is counterintuitive from the forces. Remember, a positive force, we go up, a negative force, we go down. But that's only for forces. When it comes to moments, it's actually in reverse because of the way we defined our sign convention. So if we have a positive moment, like we do in this case, we drop down. If we have a negative moment, we jump up. All right, so that's going to be the first thing. I highlighted it here in the notes so you guys really remember this. So again, this is the first thing. It's the easiest. Let's move on to the actual fun stuff. So we're going to discuss two relationships. There's going to be a load and shear relationship, and then there's going to be a shear and moment relationship. So what typically happens in this process is we take our load, we find our shear, and once we know our shear, we find our moment. So let's start with the first one. So in order to determine this relationship, we're going to take our beam and we are going to actually analyze a little element inside of our beam. Now we're going to get into a little bit of what looks like solid mechanics, finite elements, but don't worry, we're just going to come out with a nice relationship, so don't be scared once I start doing this math. It's actually very simple math. You guys are going to say, Clayton, piece of cake, I don't know why the university pays you, this is too easy. But yeah, so if we look at this here, we have our beam, and we took out a little element of this beam. Now this element is going to have a width of dx. It's an infinitesimal element. Again, very small. I just blew it up to kind of show you guys what's going on. Now, since we took an element out of our beam, we essentially cut it on both sides. So we're going to have to show its internal forces. On the left-hand side over here, we are going to say that it has a shear force going up. And again, this is because we're analyzing kind of that other side. It has a moment and it has an axial load. So again, this is nothing new. You guys are saying, Clayton, piece of cake. And on the other side, what we are going to define it as this. Our shear force on the right side is going to be equal to the shear force on the left plus the change in shear force over the length of this element. So basically the dv over dx, that's the slope, and then the dx at the end, that's the distance. We're taking slope times distance. That together is the change in shear over the length of this element. And we can do the same thing for our moment. So our moment is going to be equal to the moment on the left plus the change in moment over the length of this element. And then for our axial load, it's going to be the same thing. It's going to be the axial load n plus the change in axial load over the length of the element. What's nice here again, when we're dealing with shear force diagrams and bending moment diagrams, we usually don't consider axial load. I put it in here to make the diagram complete, if you will, but we're not going to really see it in any of these calculations, which is always nice. So the thing that we have to consider for this particular course, everything must be in equilibrium. And that's true in real life. Everything must be in equilibrium. Whether it's moving or not, that's a different story, but in this case, everything must be in static equilibrium. So the sum of the forces must be equal to 0. So if I were to look at my element here, and I were to go summation of the forces in the y direction, I basically have this equation, and it has 3 components. It has the shear on the left, the shear on the right, as well as our distributed load W. Now the first thing that we're actually going to do is we are going to cancel terms and simplify it. So if we were to look at the very beginning of our equation here, we see that the first thing that we have is we have a shear V minus a shear V. So we know that those two can cancel out right away. And once we simplify it, we get the following, where dv over dx multiplied by dx is equal to negative w times dx. Now if we look at this, we can actually simplify it even further because we have dx on both sides. So what we can do is we can say, all right, we're going to divide by dx on both sides. That gets rid of that. And we get this equation where the negative of our distributed load w is equal to dv over dx. Now, this is actually a very nice relationship that we use a lot in solid mechanics, but for Eng 130 purposes, we can rearrange it a little bit by integrating on both sides. And this leaves us with our first relationship. Our shear force function is actually the integral of our distributed load multiplied by -1. Now this -1 thing, it's kind of controversial. What usually happens is if we were to look at our distributed load, we would usually give you guys that picture and say that it's 5. And we know that based on the picture, it's going downwards. But since it's actually going downwards, we have to show that it's negative. It's technically -5 because we're going downwards. So we solve that by including that little negative sign at the beginning. Now you guys are saying, all right, Clayton, it's not too bad. But what exactly does this tell us? Well, it tells us 3 things, 3 very sexy things that are going to make your guys' lives a lot easier. The first one is the order of our shear force function is always going to be 1 higher than our distributed load because we're taking an integral. So if I have a constant distributed load, then my shear must be linear. If I have a linear distributed load, like a triangle, then my shear must be quadratic, and so on and so on. So that's kind of the first nice little thing. The second one is that the slope of our shear diagram at a point is the negative value of the load at the same point. Now this is one that you guys may not understand right away, but don't worry, we are going to show where this actually becomes extremely useful and what scenario this one is used in. It's more in moments than it is for shear, but it's something to keep in mind. Now the final one, which is going to be nice, is that the change in shear between 2 points is the negative area of the distributed load. So as we're going to see, with these relationships, we actually come to kind of a branch. We have 2 options. The first one is we can just do the integration. And that's perfectly fine. Again, you guys are very smart students. You guys will know how to do the integration very well. But there's actually a simpler method where we just calculate areas. Now most students prefer that because, well, it's easier than doing integration some of the time. I'm going to show very simple examples, which is kind of bad on my part. And you guys are going to say, Clayton, they're both easy. But sometimes it gets very difficult to do the integration. All right? Sometimes. I'm not going to say when, but sometimes. So this is why we present these kind of the 2 options. And whatever works best for you guys. It's whatever you guys want. I'm just showing you guys all your options so that when it comes to the final, you guys will know kind of your arsenal of weapons, which is basically cutting, integration, and then this third method, the area method. Now let's show this in action so you guys can kind of see what exactly is going on. So let's say I have my beam here, and this is the beam that we solved for in the previous video where we did the cutting method. So let's see how we can use relationships to make our lives easier. So of course we have our beam, and we're interested in our shear force diagram. So again, the first method, we can directly integrate it. We know that our shear force function is the negative of the integral of our distributed load. Our distributed load we know is 5. So this is simply going to be negative of the integral of 5. And this is what I'm saying in this example. Of course, it's going to be very easy. We're just integrating 5, and you guys are saying, all right, Clayton, that's going to turn out to be negative 5x. And this is why I won't recommend the integration function, because that's almost what every student does. Negative 5x. The thing that we have to keep in mind when we're integrating, yes, it's negative 5x, but we have a constant at the end. So in this case, it's plus c. So this is the thing that students usually forget, is that plus c, and then they get everything wrong and they get mad, saying, Clayton, you said it was easy. And I said, yeah, but you forgot the plus c. Now, the c actually isn't too bad to figure out. This is going to be the shear at the start of our segment. So in this case, the start of our segment is point A. So this is actually going to be equal to the shear at A. Now, how do we figure that out? Well, we look at our diagram here, and we know that at point A, we have a point load of 5 going upwards from the support reaction. So we know that our shear actually starts at 5. Again, point loads, they jump it up or down. In this case, we have a load going up, so we jump it up by 5. So we know that our actual shear equation is going to be negative 5x plus 5. And then we have it, we're good to go. We can draw it, and we say, all right, it's looking pretty sexy. And this is also reinforced because at B, we have another point load of 5 going upwards. So we know that a shear force expression ends at negative 5, and then it gets popped back up to 0. So this is how you guys know if you guys done things right. It should always start and end at 0. Always. We start at 0, we popped up 5 because of the point load, then our shear force due to the distributed load came down linearly, and then the other support reaction was 5, so we pop back up, we ended at 0. So we can shade it in and we say, all right, here's our shear force diagram. Again, no cutting was needed, and I took way too long to explain it. You guys can do it even faster than I can to explain it. Now again, some of you guys don't like integration. I get it. I'm not the biggest fan of integration myself, but it's one of those things that you have to do it at some point. But if you guys want to try and postpone all that torture, we have this nice thing here where we said that the change in shear between 2 points is the negative area of the distributed load. So what we can do is we can actually utilize this relationship here. When we do this method here, what we're going to do is we're going to start at the left and we're just going to move our way right. So again, if we look at the very left-hand side of the beam at point A, we know that we have a point load of 5. So we know that we are actually going to pop up to 5 and that our shear at A is equal to 5. Then we deal with the distributed load. And what we did is we said that we can actually find the change in shear between 2 points. So what I can do is I can say that the change in shear between point A and point B is the negative of that area of the distributed load. So what I can do is I can say, all right, well, if I look at my distributed load, it has an area of 5 times 2. Again, it's a rectangle. The height is 5, the width is 2, and then we have to include that negative sign. So we now know that the change in shear between point A and point B is negative 10. From here, we can actually solve for the shear at B, because again, the shear at B is going to be equal to the initial shear, the shear at A, plus the change in shear between those 2 points. Well, we know that the shear at A is 5, and the change in shear is negative 10. So we now know that the shear at B is negative 5. So the key here is we now know what this point is. And then we have to use our intuition. This is when we go back to that first little relationship tidbit where the order of the shear function is 1 higher than the distributed load. So if we look at this and we say if we have a constant distributed load, well then our shear function actually must be linear. So now that I know that what these 2 points are, and I know that it's a linear relationship, I can just draw it as linear. And then from there I can say, all right, well the next step is what is happening at B. Well, we have a point load of 5 going upwards, so we would draw that point load and then we end back up at 0. So notice how we have the exact same thing that we did above, but less calculations. All we did was find an area. We didn't actually have to worry about integrating anything. So we can shade this in and we say, all right, we're good to go. So that's going to be our first relationship. Again, we have 2 options. We have the actual integration or we have the area, but we're only halfway there. Again, all we did was find the load and shear relationship, but we haven't talked about moment yet. Well, it turns out their moment relationship is actually related to shear. How do we do this? Well, we go back to our fun little element of our beam. And again, we utilize the idea that the element must be in equilibrium. Now, before we said this, and we took the summation of forces in the vertical direction, summation of forces in y. But what we're going to do to find a moment relationship is we're actually going to take the summation of moments is equal to 0. And we're going to take it about this point A. So this is going to be on the right-hand side. Now, this is nice because the normal forces actually intersect through A. They're going to cancel out. It's going to become very nice and easy, but it's going to look gross. So brace yourselves. This is going to be pretty ugly to start. If I were to do summation of moments to the A, I get this expression right here. So again, the key things here is the shear forces have to be multiplied by the distances, and same with the distributed loads. Now, just like before, we are going to cancel some of the terms and simplify it. So again, the first easy one is at the start we have negative m plus m. I can get rid of those, and I can move some things to the other side to get this expression over here. As you guys are going to see, the process is almost identical to that of the load-shear relationship. Because if I look here, I now have dx in all the terms, so I can divide by dx on both sides, get rid of all 3, and then I get the following. Now this is where the first real trick comes along, and this is where I'm hoping you guys are somewhat familiar with calculus, and that is the idea that we still have a dx here. Now keep in mind that we took a slice of our beam, but if we're actually trying to integrate things, we need to take it as the limit approaches 0. So what we're going to do is we are going to take the limit of this equation as dx approaches 0. Again, we want our slice to be as small as possible. From here, this basically substitutes 0 in for dx, and we get rid of that term. And we get that our shear is equal to the change in moment over the length of our element. Now, just like before, we are going to integrate on both sides, and we get this relationship right here, which is nice and easy to memorize because it's almost identical to the previous one, where our moment function is just the integral of our shear function. It's that simple, it's that easy. We took our shear by integrating our distributed load, and now we can find our moment by integrating our shear. That's it, that's all, nice and easy. What does this mean? Well, it actually means the same things as before, but now instead of load and shear, we have moment and shear. So the order of our moment function is actually going to be one higher than our shear function. So if our shear is linear, then our moment is going to be quadratic. The second one, of course, is the slope of the moment diagram at a point is the value of shear at the same point. So again, this is something I said we're going to talk about later. And once we see in moment diagrams, this is going to become very important to you guys. And then finally, the change in moment between 2 points is the area of our shear function. So these are exactly the same as before, except now they're for shear and moment rather than load and moment. Nice and simple. So let's say that we have our shear force diagram, which we solved for before, and we want to use this to now find our moment diagram. Well, the first one, of course, direct integration, that always works. And we said that our moment function is simply the integral of our shear function, which we found in the last diagram. So I'm going to integrate negative 5x plus 5, and I get negative 2.5x squared plus 5x, and then again plus c. C always throws students off, but remember, c is going to be either the shear or the moment at the beginning of our segment. So in this case, it's going to be the moment at A, which we know is actually going to be equal to 0. Another trick that you guys always need to remember is this. If we have a pin or a roller, they never provide any sort of moment resistance. So the moment at a pin or a roller must always be equal to 0. So in this case, we know it's going to be equal to 0, and we know that our moment function is negative 2.5x squared plus 5x. So if I wanted to, I can go to my diagram, I can draw it, and see, you know what? Pretty easy, right? Yeah, again, it's not too bad, but I know that some of you guys really hate integration, so we have our second method, which is the moment at a point, which again is going to involve finding the moment at A, and then finding the moment at B, and figuring out what the relationship is between those points. So for this, same process as before, but instead of the area of our distributed load, we are now taking the area of our shear force diagram. So in this case, if we look here, we can see that it's essentially two triangles. So the first triangle, we have 1/2, because it's a triangle, of 5, which is the height, times 1, which is the width. Now I'm going to give a little asterisk here, a little note. We haven't discussed why it's 1 yet. We kind of know from intuition it's symmetric, but we're going to discuss in the next slide how we know it is actually equal to 1. So that's going to be our first triangle. Then we move on to our second triangle, and keep in mind that our second triangle here is actually negative. It's in the negative realm. So we're going to go minus 1.5 times 5 times 1. And from here, we actually get that this is equal to 0. Again, we have two triangles of equal size, except one's positive, one's negative, so we know it's equal to 0. We can say, all right, well, if I know the moment at A, and I know the change in moment between A and B, I can solve for my moment at B. So it's going to be equal to 0 minus 0. So we know that the moment at B is actually going to be equal to 0. So now we have our 2 points, and then we look at the relationship. We know that since our shear is linear, our moment must be quadratic. So students go, okay, that's nice and simple. I know that this has to be quadratic, so I know that the moment diagram must look like this. And this is correct. We know from the direct integration this matches completely, we're good to go. But here's where the trick is. And this is where that second relationship implication becomes so important. How do you know that it's that one, that moment diagram, over this one? They both have the same moment at A and B, and they're both parabolic. Well, we have to try and figure out which one it is. So again, we already knew what it was because we did the direct integration. But what happens if we didn't do that direct integration? Then we don't know. So this is where that second identity becomes so important. The slope at our moment diagram at a point is the value of shear at the same point. How can this help us? Well, let's look at point A. We know that point A has a shear value of 5, positive 5. This means that our slope of our moment diagram at point A must have a value of positive 5. And if we look at our blue distribution, it has a positive value, so it's good. If we looked at our green distribution, it has a negative value of slope to start. So this is how we know that it's actually going to be the blue one over the green one, because we have a positive slope. And this is actually reinforced if we look at point B. The shear at B is negative 5. So we know that our parabola here must have a negative slope to end. Again, the green one has a positive slope, so we know it's not actually true. So we can conclude that this is going to be our moment diagram. So again, both methods a lot simpler than cutting the beam. We end up with our points, we can integrate, it's all pretty good. Now I got a little bit of sad news for you guys, and that is this. Whether you do the direct integration or the moment at a point, you guys won't get full marks. And you guys are saying, what? What? Clayton, we did all that work, we don't get full marks? Why? Why? Well, when we're analyzing these diagrams, we have to include all critical locations. So the things that we actually forgot to do was label the maximum moment. We said it's equal to 0 at A and B, but we know that our parabola came up and came down. We didn't know what that maximum point is. So what would happen is you guys would actually lose some marks. And you guys are saying, Clayton, all right, I understand that, but how do we solve for that? Well, again, they're related because one's simply the integral of the other. And we know about derivatives, it's the minimum maximum idea. So what happens is the maximum moment actually occurs when our shear is equal to 0. So again, if we had these and we were to submit this to the professor, chances are we're getting some marks off because we forgot to include two things. The first one is the location where our shear is equal to 0. The professor's going to want to know that. If you don't do that, you're going to get some marks off. So there's the first one. And the second one is, what is our maximum moment? Now again, these look like two separate steps, but they're related because point C, where our shear is equal to 0, well, this is actually where our maximum moment occurs. So we have to do both anyway. And if you guys remember in the previous slide where we talked about how we know that these little triangles in the shear are equal to 1 in width, this is actually how we figure it out. So the first thing we're going to do is find the location of point C. Now the trick here is we know what the shear at C is. We know that it's going to be equal to 0. So all we can do is we can take our formula where the shear at C is equal to the shear at A plus the change in shear between A and C. But instead of solving for the shear at C, we say, well, we know what that is and we know what the shear at A is. We can solve for the change in shear between these 2 points. So if I were to rearrange the formula, I get that the change in shear is equal to the shear at C minus the shear at A. And we know that the shear at C is going to be 0. That's what we're trying to solve for. And the shear at A is, again, 5. So we do this, we know that the change in shear that we want is equal to negative 5. Now, we take this a step further because we say that the change in shear between 2 points is negative of the area of the distributed load. So if we look at our distributed load, we basically need to find an area that is equal to 5 because it's negative 5, etc. So all we can do is we can say, all right, since we're dealing with a rectangle, we know it's going to be base times height. The height 5 is not going to change. It's always constant. It's that width that we're trying to change. So we've got negative 5 times d is equal to negative 5. And from here, we can easily solve for d as equal to 1. So this is how I knew in the previous slide that the width of those two triangles is actually equal to 1. So typically, I would do this step before I even attempt the bending moment diagram. So one of those little things. So now that I know what this is, and I have all of my unknowns in my shear force diagram complete, I can move on to our maximum moment. So we know that the change in moment between A and C is equal to the area of our shear force diagram, which is actually simple. It's just a little triangle. So we know that this is going to equal to 1/2, because it's a triangle, multiplied by 5, because that's the height of our shear force diagram triangle, and then multiplied by 1, which is the width. So from here I get 2.5, and this actually can be substituted into our other equation. And again, we know that since the shear at C is equal to 0, this means that the moment at C and the maximum moment are actually the same. And we can solve for that by going the moment of A plus the change in moment between A and C. So we go 0 plus 2.5, well, it's equal to 2.5. And therefore, we know that our maximum moment is equal to 2.5. And that's how we do it. That's it. That's all. That's relationships for you guys. When it comes to which method you guys are using to solve these diagrams, whatever one works for you. We've shown you guys cutting. We've shown you guys direct integration, and then that area between 2 points. All three are valid. It's completely up to you guys, whatever you guys are most comfortable with. I know you guys are extremely smart students. You guys can make that decision for yourselves. So yeah, that's it for this video. I want to thank you guys all so much for listening. I really appreciate it. I will see you guys in the next lecture video.